Hello everyone, today we'll be doing problem 9.80 and this is one of the more challenging problems in the textbook. This question states that dehydration of our stirring material with sulfuric acid results in this cyclopentene as a minor product. A. Draw the stepwise mechanism to how you would form this alkene, and B. Draw other alkenes formed in this dehydration. At least one 5-member ring must be formed. So on this page, I'll show you guys a stepwise mechanism how to form our minor products, and on the next page, we'll form the other alkenes of this dehydration. So we have an alcohol, we have a strong acid, just like before. We need to show that we will protonate our alcohol, and remember I like using H plus and A minus. So the oxygen of the alcohol being nucleophilic will pick up that proton. Forming this oxonium compound here, positive oxygen, which is not favorable, not stable. So this water will just pop off to form neutral water and form a stabilized tertiary carbocation, just like before in other problems. But now we have a tertiary carbocation and we need to make this cyclohexane into a cyclohexene. So how do we do that? So on paper, carbocation chemistry is very beautiful, but in reality, carbocation chemistry can be very messy. And yes, you will have obviously majority of other products being formed, but you will have a lot of side reactions at the same time. So one of these minor products, which will occur in honestly a very, very, very small fraction and small occurrence and probability, but these products can still form. So remember, your sigma bonds, all your sigma bonds are formed from 2 electrons. And when we do nucleophilic attacks, we do nucleophilic attacks from 2 electrons. So in essence, a sigma bond sometimes can act as your nucleophile. So let me show you what I mean by that. So let's say this sigma bond right here. If I were to use those 2 electrons to nucleophilically attack this carbocation to neutralize it, I would form now cyclopentane structure with the carbocation being shifted up here. So now this is great because now we get our cyclopentane, but we don't get our cyclopentene. If I kept my carbocation up here, I would only get dye-substituted dehydration products. But that's not what we want. So if I were to use these beta protons here in blue off these beta carbons, we would get dye-substituted alkenes and not this minor product that the textbook is asking us for. So what I can do is, yes, we have a tertiary carbocation, but we can do an R-shift carbocation rearrangement, 1,2 shift, using this methyl group. So this methyl group shifts over here, then once again, we will get a tertiary carbocation, but now it's going to be within the cyclopentane. Now if I highlight the beta carbons, these are all equivalent because there's an internal plane of symmetry of this molecule, so this is achiral, so it doesn't matter which beta carbon our conjugate base takes, doesn't matter because they're all equivalent. But if our A minus or HSO4 minus picks up this proton, we make a new bond, reforming our acid catalyst. But when you make a bond, you need to break a bond, so that sigma bond will break, forming our alkene and neutralizing our carbocation, and making 4 bonds to satisfy the octet rule. And this is how we form this structure and our acid catalyst. But once again, this will occur with minimal frequency, minimal probability. More likely, though, the other alkene, so this was A, so now let's go to B. More likely is obviously using our cyclohexane here with this carbocation here. It's already tertiary, it's already stable, and we have beta carbons coming off of this carbon right here, this beta carbon right here. So our A minus can easily deprotonate that to form an alkene here to give us this other alkene product, which is a tri-substituted alkene. But now the textbook says one of these products must be 5-membered. So I will go from this intermediate, the carbocation being up there, and like I said, these carbons also have beta protons because they are beta carbons. They have beta protons, and this A minus can actually deprotonate one of these to form a di-substituted alkene. And remember, it doesn't actually matter which one it chooses because it's an asymmetric molecule. It's internal plane of symmetry, meaning it is achiral. So as you see here, I gave you guys a step-by-step synthesis of how to generate this minor product shown in the question, plus 2 other alkenes that can be formed for part B.